Hi, today I'm going to talk about innovative design method and experimental investigation of a small scale and very low tip speed ratio wind turbine. Uh, the relevance of the classical blade element and one-dimensional axial momentum theory traditionally used for the design of large-scale wind turbine operating at high tip speed ratio lambda. From this table we can see that the large-scale wind turbine with the rotor diameter larger than 5 meter and operating at the lambda within the range of 6 to 9. So the classical blade element and one-dimensional axial momentum theory is applicable on the large-scale wind turbine, whereas in the centimeter scale wind turbine, the blade element momentum theory is controversial. This is because at low tip speed ratio lambda and at low angular velocity, Reynolds number is low and high torque is required to overcome the mechanical friction. In return, a high torque induces a high rotation of the fluid in the wake and significant losses. So the blade element momentum theory does not consider the rotation of the wake induced by the rotation of the blades. Purpose of this research: so at low tip speed ratio results into a significant rotation of the fluid in the wake. So according to angular momentum balance, the torque applied by the rotor on the fluid is linked to the amount of tangential velocity. The main purpose of the proposed design method is to force the fluid to follow a geometric deflection by constraining it into a blade cascade arrangement. And the aim of this study is to investigate experimentally the performance and the wake of a 300 millimeter horizontal axis wind turbine operating at low tip speed ratio lambda is equals to 1. This turbine is designed with the new method based on blade cascade arrangement. The experimental results of the innovative wind turbine are then compared with the more classical 300 millimeter three-bladed horizontal axis wind turbine with the higher tip speed ratio lambda is equal to 3. Alright, these are the nomenclature which will be used in this presentation. This is a schematic diagram of the experimental setup. The experimental study is carried out in a frontal type wind tunnel. The turbine is mounted on a 530 millimeter tall mast with a 700 millimeter long nacelle containing a rotating shaft on which a rotating torque meter and a motor is attached. The wind speed in the tunnel is kept approximately constant uh, and it is equal to 10 meter per second. The particle image velocimetry is handled by Dynamic Studio. The flow is continuously seeded with 2 to 5 micrometer diameter drops of oil sown by a fog machine. Approximately 200 double frame images have been acquired with each wind turbine mounted and operating at their optimum tip speed ratio. And these are the cameras which have captured 200 double frame images for the both turbines. Alright, so this figure shows the relation between the power coefficient versus tip speed ratio lambda. We can see that the power coefficient um, graph for various values of tip speed ratio lambda. The power coefficient Cp is defined as the ratio of the power produced by the wind turbine to the available power, and the tip speed ratio lambda is equals to the radius of the rotor of the wind turbine times the angular velocity of wind turbine to the wind free stream velocity. From this figure we can see that the maximum power coefficient for the innovative type new turbine is 0.31 for lambda is equals to 1. and the associated power is 13.1 watt. The maximum power coefficient for the BWT, the classical type turbine, is 0.3. For the lambda is equals to 2.9. And to the best of the author's knowledge, the EWT is the first wind turbine designed to operate at lambda is equals to 1 that achieves such performance at this scale. This graph shows the relation between the torque coefficient versus tip speed ratio lambda. The torque coefficient is defined as the ratio of the power coefficient to the tip speed ratio lambda. So from this graph we can see that at low values of lambda, the torque coefficient is higher for EWT type turbine than the conventional one, and it decreased linearly with the lambda. So the high magnitude of torque coefficient at low lambda allows EWT type turbine to have lower instantaneous cut-in wind speed than the conventional turbine. So the cut-in wind speed for the EWT type turbine is 2.4 meter per second, and the cut-in wind speed for the conventional type turbine is 7.9 meter per second. And another significant thing is for a single value of torque coefficient, let's say for example at 0.1, we can have a different lambda values for the BWT type turbine. For example, at 0.1 torque coefficient, we have the one value of lambda, then we have another value of lambda, and then we can have the third value of lambda. So the one operating point is stable, and the other two points located on the transient line are unstable and lead to an acceleration or deceleration of the wind turbine until a stable regime is eventually restored. Thus, the BWT type turbine cannot operate in the whole range of tip speed ratios, whereas on the other hand, the EWT type turbine has a single lambda and has a unique operating point for its whole range of torque coefficient. This figure shows the tangential velocity fields from particle image velocimetry. Figure 5a and figure 5c is for the EWT type turbine, and figure 5b and 5d is for classical BWT type wind turbine. From figure 5a and 5c, we can see that the tangential velocity magnitude in the vortex center decreases with the distance from the wind turbine. For example, at distance z is equals to 111 millimeter, the velocity at vortex center is 6.8 meter per second, and it decreases from 6.8 to 5.6 meter per second for the second vortex center, and then from 5.6 to 4.8 meter per second for the third vortex center. The wake angle is 3 degrees, and no recirculating bubble associated with vortex breakdown have been observed in the 500 millimeter downstream. Also, the radial distance between the vortex and the rotor axis decreases by 2 millimeter for each center. This indicates that the wake is expanding behind the EWT type wind turbine. In BWT type wind turbine, the wake angle is 6 degrees higher than the EWT type turbine, where it is 3 degrees. Right. This figure shows the velocity profile of the wake for both turbines. So there is a comparison for the between the EWT innovative type wind turbine and the classical wind turbine. So the EWT innovative design wind turbine has been designed with a target tangential velocity of 6.8 meter per second in the wake in order to generate the desired power. The average tangential velocity along the span are close to the designed tangential velocity. We can see in this table at various distances from the rotor axis, when z is increasing, This is in millimeter. We can see that when the distance is increasing, the tangential velocity, the average tangential velocity from root to the tip uh, is is almost uh, similar. They are close, and the designed velocity was 6.8 meter per second. So they are close. Also, tangential velocity decreases linearly from root to tip, right? This is also an important observation. The high magnitude of tangential velocity in the wake is associated with high energy losses in the rotating wake. This kinetic energy could be recovered by a contra-rotating wind turbine placed behind the EWT type turbine. Whereas, if we talk about the BWT type turbine, the tangential velocity profiles for BWT for various distances shows a high degree of similarity. Along the span, the maximum magnitude of maximum tangential velocity is approximately 1.5 meter per second, much lower as compared to the EWT type turbine. This figure shows the axial velocity fields from particle image velocimetry. Figure 7a and 7c is for the uh, EWT type turbine, and figure 7b and 7d is for classical wind turbine. Um, so from this figure we can see that the wake expansion is more prominent and significant in the BWT type classical wind turbine. As already discussed, that the wake angle in the BWT type turbine is 6 degrees, whereas the wake angle in the new innovative design EW type wind turbine is 3 degrees. Alright, so this graph shows the axial velocity profile for the both turbines, the EWT type and the BWT type turbine. So we can see that the axial velocity profile in the for the EWT type turbine is relatively constant and is equals to 6.5 meter per second, whereas for the BWT type turbine at distance z is equals to RT by 3, which is represented with the red color, is relatively constant and equal to 6 meter per second, and the axial induction factor set for the both turbines was 0.33 for both wind turbines, whereas uh, the calculated induction factor for the BWT type turbine in the experiment was A is equals to 0.4, that is higher than the design axial induction factor. Thus the fluid is more decelerated um, than predicted by the design specification. The experimental measurement of axial induction factor vary from A is equals to 0.339 at Z is equals to 52.5 millimeter to A is equal to 0.330 at Z is equals to 250 millimeter. So we can see that the axial induction factor is not uh, changing significantly. So there is a very slight change for the EWT type turbine, and the results are really close to the design setting that prove the good efficiency of the design method. The EWT wind turbine presents a power coefficient like the classical wind turbine, but at a very low optimum tip speed ratio, lambda is equals to 1. The EWT wind turbine presents a very low current wind speed and generate high torque at low tip speed ratio that make it an efficient wind turbine for low wind speed application. To the author knowledge, it is the first centimeter scale wind turbine that achieves such performance, that is the power coefficient 0.3 and the associated power is 13 watt at a tip speed ratio lambda is equals to 1. The analysis of the wake shows that the new wind turbine induces a highly stable and rotating wake with lower wake expansion and deceleration than the conventional one. This could be useful to drive a contra-rotating rotor. Thank you.